तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Let us consider example 5, which is design a non-inverting amplifier of gain 100 if the op amp used has open loop gain of 10 to the power 5, Ri of 1 mega ohm and R naught of 100 ohm. These are the typical parameters for any practical op amp. Estimate the loop gain, feedback amplifier gain, input and output resistances. This problem illustrates the actual design involved in any amplifier using practical operational amplifier. Now you can see the circuit. It should be non-inverting amplifier, so H feedback is given. So gain should be 100. That means gain is actually 1 plus R2 over R1, where R1 is equal to R. This is actually R2. So 1 plus R2 over R1 is equal to 100. So R2 over R1 should be equal to 99. So R2 over R1 is 99. So R1 is taken as R, R2 should be 99R in order that this amplifier should give you a gain of 100. This simple design is going to work very satisfactorily in practice. Now let us find out by how much the actual gain differs from what we have designed it for because of using a practical op amp like this. So for that, we should once again write down the composite H parameter. Now we have become experts and we will introduce here the resistance, which is 10 to the power 6 ohms, okay, and let R be taken as 1K. Let R be taken as 1K, then we'll have R2 equal to 99K. So R2 plus R1 therefore is equal to 100K. So this is the choice typically. Well, how should you select these values? Obviously this resistance should be very small compared to Ri, because Ri is supposed to be infinity, and this total value of resistance should be very large compared to R naught. R naught is 100 ohms, so R2 plus R1 is taken as 100 kilo ohms, so which is quite all right, and this is 1 mega ohm. Here we have R1 coming as 1 kilo ohm. So we have chosen our values such that the feedback network is acting independently of the input and output resistances of the amplifier. In this case, therefore, Hi is nothing but 10 to the power 6 ohms. You short circuit this plus 1K parallel 99K. 1K parallel 99K. Okay. 100 plus 99. Sorry, 1K plus 99. So this is really speaking equal to 10 to the power 6 plus, okay, 0.99K. So this is it. And next, VI, okay, this current II is going to develop II into 10 to the power 6 as the voltage here, II into 10 to the power 6. Okay, so this voltage V is going to be multiplied by 10 to the power 6 or 10 to the power, how much is it? Op amp gain 10 to the power 5 times V. So you can see that I into 10 to the power 6 is this voltage V. That into 10 to the power 5 is the gain. I into 10 to the power 6 is the input voltage V. That into 10 to the power 5 is the voltage appearing there. That divided by 100 ohms is the output current. Okay, this I divided by input current is the current gain. So we'll get this as the output current gain, output to input current gain, current ratio. So the polarity of this, you can once again see here, this is plus minus, this is positive, okay, and the current will be going in, so this is positive. The other current gain is due to II going there. 1K by 1K plus 99K will go, okay, in the opposite direction there. So minus, okay, 1K by 1K plus 99, 1 by 100 of this. So this is going to be negligible factor. Just let us test it out here again. This is plus, this is minus. I into 10 to the power 6 is here, okay, and this is 10 to the power 5 times this voltage V, which is I into 10 to the power 6. So if this is also going out. So we have this also negative. This current also is going out, this like this current, short circuit current. So this can be neglected, this can be neglected compared to this. So you are straight away neglecting it instead of carrying it over. Next, the output is open circuited and apply a voltage at this point. So feedback factor is 1 by 1 plus 99, that is 1 by 100. Then the output admittance is 1 by 100, output admittance of the amplifier, plus 1 by 100K. Once again, this can be neglected compared to 1 by 100. So essentially, you can see that the matrix parameter will be approximately this, 10 to the power 6. This is 1 by 100. This is important. 10 to the power 5, 10 to the power 11 divided by 100, 10 to the power 9. This is 1 by 100. So these are the H parameters of the composite network. So let us now find out delta H. You know that this is negative feedback because this is the loop gain. Let us say loop gain. We have been asked to find out the loop gain. This into this divided by this into this. So 10 to the power minus 10 to the power 9 by 100, 10 to the power 7, 10 to the power 6 by 100, 10 to the power 4. So 10 to the power 3. 1000 is the loop gain. It's easily discernible here. The gain from here to here is 10 to the power 5. The gain from the attenuation from here to here is 1 by 100. 10 to the power 5 into 1 by 100 is 10 to the power 3. So it is very clearly seen here because these resistances are not loading the feedback resistances. Right? So that is why it can be straight away seen that Ri and R0 do not really affect the loop gain much. Whatever is affecting is coming as extra parameter which is negligible. Right? So delta H is nothing but this into this, that is 10 to the power 4, plus 10 to the power 7. Once again we can neglect this compared to this. So 10 to the power 7 is delta H. So what is the modified G parameter here? So I divide by delta H throughout. So let us first do that. Here this is brought over here, 1 by 100 divided by delta H. Here this was 10 to the power 6 divided by delta H. Here minus this divided by delta H, here plus this divided by delta H. Simple. So the modified H parameter now becomes, what does it mean? The input impedance or in of the feedback amplifier is straight away given by 1000 mega ohms. Original input impedance was 1 mega ohm. Loop gain was 10 to the power 3. So loop 1 plus loop gain into original impedance, that is clearly 1000 mega ohm output. That is straight away given by 10 to the power 6 by 10 to the power 7, that is 0.1 ohm. See how low output impedance has become, almost an ideal voltage source, 0.1 ohm. Original output impedance was 100 ohms, that divided by 1 plus loop gain, that is 10 to the power 3 is the modified thing, that is it. So these things can be easily evaluated. You don't have to really do this by this method. This method only tells you that certain things may become negligible compared to certain other things. Such approximations can be done here, and then you can go ahead with our usual definition for feedback modification. Everything gets modified by 1 plus loop gain. So the gain, that is the important factor, voltage gain after feedback becomes very nearly equal to 100, which is originally the feedback factor was 1 over 100, and inverse of the feedback factor becomes the voltage gain. So this is the answer to this. So you can see how we can arrive at the performance of a feedback amplifier by actual evaluation of the feedback parameters, composite parameters, and converting the matrix into from H to G. So we'll work out another problem for Y feedback so as to understand once again the approximations involved. Next, let us design a trans-resistor amplifier of 10K using operational amplifier. Trans-resistor amplifier with trans-resistor value being equal to 10K. Using amplifier op-amp with A naught equal to 10 to the power 6, Ri equal to 1 mega ohm and R naught equal to 100 ohm, same op-amp that we had used earlier. Determinates input and output resistances as also the loop gain. Okay. So, V naught, this is the arrangement, this Y feedback has to be applied in order to get a trans resistor amplifier Y feedback. So, in this case I will flow through entirely this 10K we have seen, this becomes virtual ground and the output voltage becomes minus 10K II. This is ideally the output. Now, because of the finite input impedance, this is 10 to the power 6 and finite output impedance, that is 100 ohms, and the gain here, okay. So, that is 10 to the power 5, oh sorry, we will give it as 10 to the power 5, same as before. Okay. So, we can now evaluate its, if this is V, okay, the voltage here is 10 to the power 5 times V, right. So, is it clear? Fine. Now, this is let's say Vi, this is. Once again, the parameter, composite parameter that we have to select will be the Y parameters of the composite network, which we had in the last class also determined very quickly. So, as far as the feedback network is considered, it will give a Y parameter of 1 over 10K at all points, right. Input admittance, output admittance. So, 1 over 10K, 1 over 10K. This is the short circuit, and here minus 1 over 10K, minus 1 over 10K. Because this is RF, we said an RF connected between output and input will contribute 1 over RF, minus 1 over RF, minus 1 over RF and 1 over RF as admittance parameters for the whole feedback configuration. As far as the amplifier is concerned, okay, at the input this 1 over 10 to the power 6 comes into picture. At the output, this 100 ohms will be coming into picture. So, you can see that at the input this has negligible effect on this, right. So, this can be ignored, right. At the output, RF has negligible effect on this. So, this can be ignored. As far as feedback is concerned, only the passive network contributes, active network does not contribute. As far as forward transfer parameter is concerned, if Vi is this voltage, okay, we have actually speaking, this is applied to the inverting terminal. So, this will be, okay, minus plus times, okay, this voltage, this is plus, this is minus. So, if this is V, this is minus plus plus, okay, plus minus times 10 to the power 5. So, we have the current instead of going out coming in, okay. So, this is positive. So, 10 to the power 5 times V divided by 100. Okay? That is the output current contribution, short circuit output current, apart from the current due to 10K. So, you have this negligible compared to this, right. So, we will remove that, what is negligible. So, this matrix really helps you in coming up with the right type of approximation, okay, for the circuit. So, the composite Y parameter just becomes this. So, we can now find out the loop gain. Is minus 10 to the power 5 by 100, 10 to the power 3 into, okay, 10 to the power minus 4, right, 10 to the power 3 into 10 to the power minus 4. Here 10 to the power minus 4 into 10 to the power minus 2. So, this is minus 10 to the power 5 loop gain. Remember, in the yesterday's class we had done the same thing and we got the open loop gain as the loop gain for this thing. It is always the case. Open loop gain is 10 to the power 5 and very nearly the open loop gain is the loop gain of this structure. Right. So, you can see that coming from here to here, the loop gain is 10 to the power 5. This is open, right, very nearly open. So, loop gain is 10 to the power 5. It is visible there. So, then delta Y is nothing but this into this plus this into this. So, this into this is 10 to the power 3 into 10 to the power minus 4 plus 10 to the power minus 4 into 10 to the power minus 2. This can be ignored in the delta H, right. So, it is 10 to the power minus 1. Delta Y is 10 to the power minus 1. Modifying all these parameters now into Z parameter. So, we can just put 1 over 100 by 10 to the power minus 1 and this one is 1 over 10 to the power 4 by 10 to the power minus 1. So, that becomes that this is nothing but 1 over 10. This is nothing but 1 over 10 to the power 3, right. So, then this becomes plus, okay, into 10 to the power minus 1, right. This is also 10 to the power minus 1, okay. So, that, so we get here 10 to the power 4 as expected. What should it be? It should be nothing but, of course, this is negative, okay. This sign I have already changed, I suppose, right, is positive. So, you can see here this is nothing but ZF, that is coming out to be exactly what we wanted, and this is nothing but input impedance, which is of the order of 0.1 ohms, output impedance, which is of the order of 10 to the power minus 3 ohms. So, this is current control, okay, voltage source. I mean, this we could also conclude by the loop gain. Loop gain was 10 to the power 5. So, original input impedance was 10 to the power 6. So, that has to be reduced by loop gain, 1 plus loop gain. So, it is going to be what is it, 10 to the power 6 divided by 10 to the power 5. Oh no, original input impedance was actually 10 to the power 6 shunted by 10 to the power this 10k, right. So, this has negligible effect. So, 10k divided by this 10 to the power 5, which is going to give you 1/10 of an ohm. Original output impedance was 100 ohms shunted by again 10k, which was 100 ohms divided by 10 to the power 5, which is going to give you 10 to the power 3, 1 over 10 to the power 3 ohms. So, you can see that all these modifications take place by the factor of 1 plus loop gain. So, we have now designed a transconductor, which is a very useful element to convert a current into a voltage. So, now consider the positive feedback configuration that we had started in the yesterday's class. Positive feedback is a situation where the loop gain is positive. That can also be depicted as a situation where the feedback voltage is aiding the input voltage and together is appearing at the actual input of the amplifier. Negative feedback is the situation where actual input is opposed by the feedback voltage and a reduced voltage appears at the input of the amplifier. So, under this situation we saw that the gain is going to be minus A by 1 minus A naught beta. A naught is the DC gain independent of frequency. So, instead of A we will put it as A naught. We are now considering A naught as a number, right, 10 to the power 5 or 10 to the power 6 or something like that. So, beta is R1 by R1 plus R2 attenuation factor, this by the passive network. So, the gain of the amplifier after feedback is going to be minus A naught by 1 minus A naught beta. This is positive feedback situation, and we said consider beta equal to 0. There is no positive feedback. Then it is open loop. V naught is equal to minus A naught Vi. That is the situation depicted here. The slope is minus A naught at the origin, where Vi is 0, and please note the fact that when Vi is 0, V naught is 0 here. When Vi is 0, V naught is 0. That is the case always with negative feedback. When Vi is 0, when there is no input, output is 0. We are using plus minus power supply here, so that the quiescent output voltage is 0. There is no offset. So, plus minus supply voltage is applied. Then the saturation points will be plus Vs and minus Vs. So, amplifier is saturated here, is in the active region here, is once again saturated here. So, this is the active region. With negative feedback, obviously the gain is going to decrease, that we saw. It becomes A by 1 plus A beta, right. For A beta greater than 1, much greater than 1, it becomes 1 over beta. So, that is a different situation. Now, we are considering the positive feedback situation. So, this is a case where it is open loop. If I give more positive feedback, then I will come into a situation something like this. This is for A beta less than 1. That means actual gain is going to be more than the open loop gain. The slope is going to be more. Ultimately, at A beta equal to 1, it will be exactly this. the ideal amplifier characteristics. Gain is going to be infinity. That means that is a very difficult situation. If gain is infinity and I multiply it by 0, I cannot say what the output is. That means output can be any voltage between plus Vs and minus Vs, because it is vertical, right. When Vi is 0, output cannot be specified because it is infinity into 0 situation, right. Infinity is multiplied by 0. Okay. So, output can be anything between. So, that means for an input, okay, of 0, you cannot even specify the output. So, the system is going into unstable situation. As long as V naught is multiplication of Vi, you have a stable amplifier situation, even if it is minus A naught by 1 minus A naught beta. But now, even for Vi equal to 0, nothing is applied, output is not defined. So, system has gone into unstable mode of operation, but it is very useful for other applications we will see, because the actual gain has been made infinity here, and it is the transition region is very specific. It is suddenly transiting from plus Vs to minus Vs, okay, at precisely Vi equal to 0. So, you can therefore use it for what is called zero crossing detector, right, because for a voltage which is less than 0, it is plus Vs, for a voltage which is greater than 0, it is minus Vs. So, it can tell you exactly when the voltage is crossing 0. Okay. So, in a situation of comparator, this positive feedback becomes useful. Otherwise, in an actual amplifier, this is never used, because this is very sensitive to variation in A naught. Okay. The feedback gain is very sensitive to variation in A naught. Okay. And therefore, for positive feedback amplifiers, it is never used, but for comparators, it can be used with positive feedback. Now, consider the situation where this is a situation with A beta equal to 1, this line. Okay. Now, A beta greater than 1. Once I say there is no correlation between output and input, okay, output is not specified for a given input, okay, then I cannot any longer use any equation like this. That means this equation is not valid, okay, for A naught beta equal to 1 and greater than 1. So, this equation is not any longer valid. Output now is going to be, after A naught beta greater than 1, this is called regenerative feedback. Regenerative. What does it mean? I will give an example of a situation like this. This is a flat area, let us say, and we have a person here standing. Now, if you push him hard, okay, he will move quite a distance. If you push him slowly with a very little force, he will move very little, depending upon his weight. Right? That means the movement of this person, okay, depends upon the force here and the weight here. Okay. But after the force is removed, he will remain stably in that position. So, the position of this person is stable. Okay. Why? It is dependent upon the force, right? If the force is considerable, he will move a considerable distance, after the force is removed, there he will be stable. Okay. So, this is a stable situation. Consider so, this person now was originally here, this is the flat surface, right. He has been pushed to this place, okay, or this place somehow. Now, he can balance here, no problem, right. He can balance here, but the least amount of disturbance, okay, just a small impulse, it need not be kept at all, right. Just a small impulse on him, just okay, a push will be sufficient. Thereafter, he is going to destabilize himself on his own, because if his weight is okay, too much, right, he cannot balance at all thereafter, right, he will come down on his own by his own weight, right, if there is a disturbance. Okay. So, this is the stable position, this is an unstable position. An unstable position, okay, cannot be retained by the individual for any length of time. The least amount of disturbance will take him on to a stable position here. Okay. So, this is the situation of regenerative feedback. Okay. What does it mean? Let us consider in terms of, let us assume that Vi is 0. When Vi is 0, I just told you that even if A beta is equal to 1, output need not be 0. Output can be anything here. But consider the situation where A beta is greater than 1. If there is small disturbance here, that is multiplied by A naught times, that is attenuated by beta times. Since A naught into beta is greater than 1, even that disturbance, okay, after going through the loop comes out as a higher disturbance. It is indication of initial disturbance has been removed, tap. After the tap, that disturbance has been removed, but the movement here, okay, is generated by his own weight, okay, and a small movement here will force him to further move, okay, the momentum increases. So, he will move down on his own. Same thing happens here. A small disturbance, whether it is positive or negative, let us assume that it is 1 microvolt disturbance, that can happen even by just switching on some power source, right. That 1 microvolt disturbance will be amplified by A naught and beta, appearing at that moment as a value which is greater than 1 microvolt. So, let us say 2 microvolts of the same polarity. So, 2 microvolts will get further amplified. So, it will go on moving in the same direction, and ultimately it will go to the maximum possible here, that is the saturation. So, if I have started with positive 1 microvolt, it will go to positive saturation. If I started with negative microvolt, it will go to the negative saturation. I cannot therefore say if Vi is 0, at what point output is going to be. It could be either minus Vs or plus Vs. That much I am sure of. It cannot be any voltage between plus Vs and minus Vs. As long as it is in the active region, it is moving always. Okay? So, the moment this amplifier is brought into the active region, that is this region, there it is equivalent to coming to a slope. It will then come to, okay, either plus Vs or minus Vs, both which are the stable states of this amplifier. So, this is called regenerative feedback. If A beta is less than 1, okay, you will see that all these points, feedback voltages should be simultaneously existing, right, which means A beta less than 1, okay, the series which is 1 plus A beta, okay, plus A beta squared, etc., will become a stable output. Okay. As long as the input is there, output will be stable at a certain value. The moment input is removed, output will go off. So that is why in the case of ordinary positive feedback where A beta is less than 1, okay, output is stable. Whereas in the case of positive feedback which is regenerative, which is A beta greater than 1, okay, the disturbance itself is causing disturbance in the same direction, okay, which is more, such as to further move it, okay, in a direction ultimately leading towards a stable state, which is either plus Vs or minus Vs, depending upon the initial disturbance. So this is the case. Let us consider that A beta is very much greater than, okay, 1, but it is regenerative positive feedback. Now we will discuss it in this manner. What I am saying is, as long as Vi is 0, output of such a regenerative feedback network can only be in two states, either plus Vs or minus Vs. In the case of positive feedback with A beta less than 1 or negative feedback, output is equal to 0 when input is 0. Okay. This is the difference between regenerative feedback and positive feedback, which is non-regenerative, and negative feedback. Is it clear? Now, that circuit, this circuit with positive feedback is properly known as regenerative feedback. Is known as, what is it? Schmidt trigger, a very important circuit, okay, particularly in digital domain, right? Because it has no place in analog domain, because output is either high or low, whatever be the input. And such a circuit is very suitable for an interface, okay, situation. This is called Schmidt trigger. So a circuit with positive regenerative feedback is popularly known as Schmidt trigger. I mean, please understand why it is called trigger. The disturbance can be generated by applying a small voltage disturbance, okay, or current disturbance, such as to make it go into the active region. Thereafter, it will always go on its own, okay, without further change in voltage from one stable state to the other stable state. That is why it is called Schmidt trigger, right. So the disturbance is appearing as a trigger. Now let us understand this better, the regenerative feedback. As I told you, output of this, as long as A beta is greater than 1, now we have concluded for Vi large negative, let us consider Vi large negative, output has to be positive saturation. For Vi large negative, output has to be positive saturation. So this is plus Vs. For Vi large negative, output is at plus Vs. If this is at plus Vs, this will be at what? Beta Vs. Now, when will this enter active region? When Vi comes close to beta Vs, then only it will enter the active region. We have told that if A0 is very high, it will enter active region only when this voltage becomes very close to this voltage. So this will go into regenerative feedback mode the moment Vi comes close to beta Vs, right. Until that time, output will be at plus Vs. So this is going into regenerative feedback mode, and thereafter it will go to what? The least amount of disturbance will take it from plus Vs to minus Vs. Now, this is a very important phenomenon. Just see, The regenerative feedback comes into action only when this voltage comes close to this voltage. Thereafter, it changes state from plus Vs to minus Vs. This goes to from beta Vs to minus beta Vs. So, this voltage has changed to minus beta Vs. Now, if this voltage decreases, it will not change state at plus beta Vs. The voltage with which it is compared is minus beta Vs. So, it will go on, okay, like this, go on like this, and will change state only at what? Minus beta Vs. So, this is what is called hysteresis, right. The circuit has memory. The circuit has memory. Why is it? Our amplifier circuit does not have memory. Output depends upon the instant of magnitude of voltage at that instant of time appearing at the input. Here, output depends upon whether the input is increasing or input is decreasing. Because if the input is increasing, it says I will change state only at beta Vs. If the input is decreasing, it says I will change state only at minus beta Vs. So, if it is increasing or decreasing, what does it mean? It has memory, because how does it know whether it is increasing or decreasing? Only if it knows its previous state compared to present state, it will know whether it is increasing or decreasing. That is why it has memory, right. So, this is an important circuit block, semiconductor memory it is also called, right. After the advent of this, things got revolutionized. You could think of a computer in a chip, okay, only because of the existence of semiconductor memory. Prior to that, such a characteristic was being exhibited by what is called magnetic core, okay. So, this was very complicated, because for memory you used to use magnetic core, and for other processes you use active devices like transistors, okay. The moment we had this being made available, we could store information here, right. So, we have a very important circuit element, that is Schmitt trigger. This characteristic is called the hysteresis, okay, and the extent of hysteresis depends upon beta, A beta, right. So, if A beta is made much greater than 1, then specifically if you actually join this slope, which has no physical meaning, this has no physical meaning, this slope is going to be 1 over beta, obviously, right. So, in fact, that expression you see minus A naught divided by 1 minus A naught beta should not be used, okay. But if A naught beta is much greater than 1, it is becoming 1 over beta. It just indicates if you join these corner points, okay, the slope is 1 over beta, okay. Corner points of transition from one state to the other state. This particular circuit has numerous applications in digital circuit for wave shaping, that you have data transmitted in terms of ones and zeros. So, this data, when it is transmitted through the cable, gets distorted, okay, because of the distributed effect of capacitors, etc., and gets attenuated, etc., and therefore gets distorted, and you want to reshape it, okay, so that the transitions of the pulses become very sharp. So, converting the pulses which are out of shape into pulses which can become, okay, ones with sharp edges, the Schmitt trigger is always used. So, this is the entry point into a circuit, okay. All the data transmitted pulses should come through a Schmitt trigger before they are processed further in any circuit. Otherwise, okay, triggering becomes virtually impossible. Okay. So, this is a circuit which is very commonly used in digital circuits. Okay. In analog circuits, in the sense we can use this also for square wave generator, okay, etc. We will see the application of this in the next class.